All right, chemistry class, let's look at the review questions for chapter 12, and I'll walk through these with you, and we'll double check to see if we understand all these concepts. Okay? Remember, in this chapter we are talking about solutions. So solutions are mixtures, things that are going to be mixed together. They could be a solid and a liquid. They could be two liquids. They could be two gases. They could be two solids. They could be a gas and a liquid. So basically you're taking two states of matter or the same states of matter and mixing them together. All right, let's look here at number one and we'll answer these together. It says, given an unknown mixture consisting of two or more substances, explain how to determine whether the mixture is a solution, a colloid, or a suspension. Well, if you remember, one of the tactics or methods in order to kind of test to see how big the particles are, and that's really the main difference between these, how big are the solute particles in your solution, is to take a light, okay, if you take like a flashlight here, and you beam light through that particular solution, or that particular mixture, I should say, if this mixture, all right, let's say we've got a liquid solvent, and in there you put a solid solute, okay, so you've got some solid in there. If those particles of the solute, if they don't mix really well and they're still fairly large, when you shine light through here, those particles are going to scatter the light, and some of that light is going to come and hit your eye, and you're going to see that light beam. So with a suspension and a colloid, the particles are bigger, and so they are going to cause the light beams, these light rays, to spread out and to diffract, and so you're going to see them. But in a solution, the particles are so tiny that they let the light just pass straight through. You will not see any light beam if you pass that flashlight light through a solution. So that's the difference. Here you're going to have the Tyndall effect. It's called Tyndall effect. Okay, but here you will see no light beam. Okay, so that's one way to test to see if they are solution, colloid, or suspension. And again, each of those are named that way and are separated or categorized that way depending upon the size of the particles of the solute. Explain why suspension is considered a heterogeneous mixture. Well, if you remember, suspension is something that if you let it sit over time, some particles are going to settle out. So maybe I gave the example before of like some muddy water. If you shake it up, it looks like it's all uniform throughout, maybe the same color, but if you let it sit for a while, those big particles are going to basically settle to the bottom. Not all of them, but the larger ones are. They're going to be pulled by gravity down to the bottom of the container. And so a suspension is not uniform throughout because those larger particles basically will separate themselves. And so if you were to take a sample from this area right here in the solution, or I shouldn't say solution, but in the suspension, that's going to look a little bit different than if you were to take a sample of the suspension down here at the bottom. It might have larger particles down there. So heterogeneous means it is different kind, different throughout the particular suspension. All right, number 3 says, does a solution have to involve a liquid? Well, no. It might often. We can have a solution that is a solid dissolved into a liquid. That's a common one. That's like dissolving salt or sugar in water. But you can also have a solid, and I won't say dissolved, but I'll say mixed into another solid. And that would be like an alloy. So like gold and silver mixed together to make certain jewelry, or gold and copper, silver and copper to make certain types of jewelry. Or you could have a gas dissolved, this time dissolved into a liquid, like carbon dioxide dissolved into your carbonated beverage. Okay? You could have a gas mixed with other gases, like our atmosphere. You've got nitrogen, oxygen, hydrogen, helium, and other gases that are mixed together. Okay? So solution here does not have to have a liquid involved. Like I said, you could have a solid mixed with a solid or a gas mixed with a gas. Often it does have a liquid involved. We think sometimes, we kind of associate the word solution with involving a liquid, but it doesn't have to. Okay? Number 4, what is the difference between an electrolyte and non-electrolyte? When you create an electrolyte, what you're doing is you're taking an ionic compound and you are dissolving that in some solvent, usually like water. Okay, that's going to go into, let's say, some liquid water. And because it is ionic, the water molecules, and because the water is polar, are going to surround the different ions and pull them apart and separate them. Okay, so for example, if you take sodium chloride, this is an ionic compound, a metal, sodium is a metal, and a non-metal. That's how you always know it's an ionic compound. And if you put that in water, the sodium is going to get surrounded by water all around it, and as a result, it is going to separate from the chloride ion, which over here is going to be surrounded by water as well. So the chloride is going to have a negative charge because it has a higher electronegativity than the sodium. It's going to pull the electrons towards it. It's a smaller atom as well. It's a smaller radius, and so it's going to pull in those electrons closely. The sodium is going to lose that electron, that one outside valence electron. So this is going to be a positive charged particle. This is going to be a negative charged particle. You have now what is called an electrolyte, a solution that has ions in it. And that solution can actually allow for an electric current. So current, electricity, can flow through it. Why? Because you've got charged particles. These charged particles are going to allow for the passage of an electric current. Okay? So that's one difference, is an electrolyte is a solution that actually water, if it has a lot of electrolytes in it, can conduct electricity. Okay? A non-electrolyte would be maybe something like sugar. Sugar dissolved in water. Sugar is not polar, it's not ionic, it is covalently bonded, sharing electrons. If you take sugar and you dissolve it in water, you are not going to form ions. You're not going to form, it's not going to break apart, dissolve apart and break apart into ions like this did over here. The sugar is just going to dissolve into smaller and smaller particles until you maybe get down to the molecular level, and one molecule of sugar is surrounded by a bunch of waters, and so you're dissolving this. But there's not going to be any charges, no ions involved, and so this is a non-electrolyte. Okay? All right. And this would not conduct electricity. A non-electrolyte does not conduct electricity. Okay? All right, number 5. What is solution equilibrium? Well, remember, equilibrium in itself means that there's going to be a balance. And we'll talk about what is in balance, what is going to be the same here, and what factors determine the point at which a given solute-solvent combination reaches equilibrium. Okay, when you have a solution, okay, again we have a beaker here, and we have some water, and we put in, let's say we're going to put in some salt, table salt, sodium chloride. Okay, we put in some sodium chloride, and it dissolves into tiny, tiny, tiny particles. You don't see them. The water appears just as clear with sodium chloride in it as it did with no sodium chloride. So what happens here is the sodium chloride is dissolving, dissolution. It's going through a dissolution process. But if you put a lot of sodium chloride in here, you're going to start to see sodium chloride crystals down here at the bottom. You'll actually see them because you have reached a saturation point. If it is saturated, what that means is you have reached a maximum amount that can be dissolved, a maximum amount of sodium chloride that can be dissolved in this quantity of water at this temperature. And so what's happening is, yes, there's still a lot of activity. If you're able to see it, what's still happening is some of these sodium chloride crystals down here are dissolving, but also some of them bump into this pile of crystals and they recrystallize. Okay? So there's crystallizing and there's dissolving. And these two processes, when you have a saturated solution, are in equilibrium. I should say the rates of those two are in equilibrium. So the rate of dissolving is equal to the rate of crystallization. These two are equal to each other when you have a saturated solution, and we call that solution equilibrium. Equilibrium. What is equal? Not the amount that is dissolved and the amount that is crystallized. It is the rate at which the dissolving is happening and the rate at which the crystallizing is happening. Every time something dissolves, something is going to recrystallize. It's going to be like for one. The rate is going to be the same. Okay? Well, what are some of the factors that determine the point at which equilibrium is reached? Well, certainly it depends on this particular solute. I chose sodium chloride. So there's a certain amount of sodium chloride that can be dissolved in that quantity of water. But what if I chose something different? What if I chose magnesium chloride? Well, then the amount is going to be different, the amount that can be dissolved. So one factor is, which solute am I choosing? Okay, which solute? The other factor is, I said this is water. Well, what is another solvent that I could use? Maybe I could use a different solvent, some other liquid to dissolve. Okay? And the other thing I mentioned, remember, that at this temperature, I said this amount of water at this temperature. So the temperature also is another factor that might determine, or that would determine the equilibrium point. Okay? All right, number 6. It says 2 bottles of soda are opened. One is cold, the other is room temperature, a little warmer. Okay? Which bottle would show more effervescence, meaning more bubbles as a result of the carbon dioxide dissolved in the water, in the beverage? Well, you must remember that more gas dissolves at colder temperatures. Okay? So the colder the beverage, the more gas will remain dissolved, or that you'll be able to dissolve. Okay? So warmer beverages are going to lose that gas. The gas is not going to stay dissolved because it's going to have, those gas particles are going to have more energy and they're going to want to escape. And as a result, a colder beverage is going to have more gas staying in the beverage. You will not see the bubbles. So a warmer one, the warmer beverage will release more bubbles. That's what is meant by effervescent. Okay? So it'll be more effervescent. All right? Warmer beverage will have more bubbles released. We say it is more effervescent. The colder beverage will retain more of that gas dissolved in it. Okay? That is for a gas. A colder liquid dissolves more gas. That is not true for a solid. It's the opposite. A warmer liquid will usually dissolve more solid, but for gas it's the opposite. Okay, number 7. What rule of thumb is useful for predicting whether one substance will dissolve in another? Describe what the rule means in terms of various combinations of polar and nonpolar. So the basic rule of thumb is like dissolves like. What does that mean? Like dissolves like. It means that a polar solution, remember what that means is that the particular molecule has electrons spending more time on one side than the other side. And as a result, it has a negative end to the molecule and a positive end. The overall molecule is still neutral, but one end is going to be more negative, one end is going to be more positive because the electrons are being pulled to one side a little bit more because of either the arrangement of the structure, the geometry of the molecule, or the types of atoms that are involved. Okay, so polar dissolves in polar. That's what we mean by like dissolves like. And non-polar, meaning molecules that don't have a negative and a positive end to them, non-polar dissolves in non-polar. Okay? That's what we mean by like dissolves like. Alright, number 8. What visible evidence indicates that a solution is saturated? If a solution is saturated, you will know because that particular solution is going to have some crystals down here at the bottom of that particular solute, whatever, let's say, solid you're dissolving in there, and they will never go away. It doesn't matter how much you stir this, doesn't matter how much you shake it. If you added more water, or whatever solvent you have, then yes, that would change. Or if you increase the temperature, yes, that would change. But if you don't change the amount of water, let's say that's your solvent, or change the temperature, you will have crystals down here if it is saturated. Okay? Now, you might be at the perfect point of saturation and you may not see any crystals, but if you add even just a little bit more salt or sugar or whatever you're using, you would see those crystals at the bottom here because no more would be able to be dissolved. Okay, so that's your visible evidence, is you see crystals that are not dissolving because it's already maxed out. It is saturated. Okay, number 9. If the pressure of a gas above a liquid is increased, what happens to the amount of the gas that will dissolve in the liquid if all other conditions remain constant? Okay, if you remember, we talked a little bit about this, I think, with like a bottling company. Oh, nice bottle. All right, that's terrible artwork there. Sorry about that. Okay, so this is my bottle, and it's capped, all right? And you have a liquid in here that has some gas particles dissolved in it. Can't see them. And above, you have the same gas, a lot of the same gas up here, creating pressure in this little pocket here, in this little space. And that is going to cause pressure here, is going to cause it to keep the gas dissolved. The more this pressure, the higher this pressure, the more gas you're going to have dissolved in this liquid. Okay? So the relationship is simply this. As pressure increases, dissolved gas, the amount of dissolved gas can increase as well. Okay? All right, number 10. It says use the solubility versus temperature graph in section 2 to determine the solubility of each of the following in grams of solid per 100. First of all, let's make sure we just talk a little bit about solubility, what we mean by that. Solubility is a measurement to look at how much can be dissolved, and usually it is per 100 grams of the solvent. In this case, the solvent is water. So what mass, how many grams of a solute can be dissolved in 100 grams of water? And this is saying we're just looking at a graph. That graph is going to just show us, and we can just look at the chart and figure it out. And notice it is a solubility versus temperature. Now remember, we said for solids, all of these are solids here, these are all actually ionic compounds, ionic solids, that usually solubility is going to go up as the temperature goes up. The warmer the water, the more that warm water can dissolve. Okay? So if we look back in section 2, we look at this graph, we're just going to point out a few things, and then I'll let you just read the graph and be able to put down the value. Okay, we'll look at one together and then you can do the other two. So we'll look at sodium nitrate at 10 degrees Celsius. So let's go back up to section 2. Okay, here we are. Here we have sodium nitrate and 10 degrees Celsius. All right, all I do is from 10, I go up to the particular curve for sodium nitrate. Looks like it's right around there. And then I go over to solubility in grams. And it's going to be around 80 or so. Okay, maybe a little bit more than 80, that's 90, maybe 82 or something like that. So about 82 grams can be dissolved in 100 grams of water. 82 grams of sodium nitrate can be dissolved in 100 grams of water at 10 degrees Celsius. Okay, at 10 degrees Celsius. And you would just look for the others. So you just find whatever ionic solid you're looking for and the temperature you're looking for, go up to that particular curve and then over to find out the mass that can be dissolved. Okay? So this was, what did I say, 82 grams or something like that. So you can do B and C on your own. Okay? Okay, number 11. It says the enthalpy of solution. That is the heat to dissolve. The heat to dissolve. Is there heat that's going to be released when we dissolve something? Is it exothermic? Or is heat going to be absorbed when we dissolve something? Is it endothermic? And here it says the enthalpy of solution of silver nitrate is positive 22.8 kilojoules per mole. If the enthalpy is positive enthalpy means energy absorbed. Energy is going into the solution. That means it is endothermic. Endothermic. Okay? Positive means the direction of the energy flow is into the solution. So, absorbing energy. As silver nitrate dissolves, how does the temperature of the solution change? Well, if it is pulling energy in, then it's going to feel cold. If you touch that, all right, if you were to touch that container, if it's pulling energy from your fingertips, wherever it can get it, from the atmosphere, the glass container, your hand if you're holding it, it's going to start pulling energy from that in order to help the dissolving process. So it's going to feel cold. So the temperature is going to go down. The temperature goes down as a result. Okay? I know it's kind of weird to think that temperature is going down when it's pulling energy in, when it's pulling heat in, but you have to remember it is you need that energy in order for the dissolving process to occur. And temperature is measuring the average kinetic energy of the particles. So if you were to take a thermometer that's maybe at room temperature and you put that into the solution and it starts to pull energy away from that thermometer because it's warmer than the solution, or it needs that energy to dissolve, then the thermometer liquid is going to actually lose energy, and the temperature is going to be measured at a lower value than it was before. Okay? So the temperature is going to go down of your solution as it absorbs more and more energy from the surroundings, from the environment. How do the rates of dissolution and crystallization compare at equilibrium? They are the same. We said that before. They are equal. Okay? So at equilibrium, the dissolution and the crystallization rates are the same. All right. If the solution is then heated, how will the rates of dissolution and crystallization be affected? Well, if you heat this up, this particular process wants heat. It likes to absorb heat in order for this process to occur. So if you were to increase the heat, all right, then it is going to be able to dissolve more. because that's what it likes. It wants more energy, it wants heat in order to encourage this dissolving process. So the dissolution is going to increase as a result. All right? And then you could probably add more and more if you wanted to. You could add more silver nitrate, and then it would get back to equilibrium. Okay, and then again, the dissolution and the recrystallization process, those two processes would have the same rate. But initially, if you heat it up, it's going to be able to dissolve more. Okay, especially because you notice here, it's adding energy. You're adding energy. So if you add more, it's just going to encourage this dissolution process. Okay. And you'll be able to dissolve more. The solubility, the amount, okay, the solubility, the amount of grams of silver nitrate will go up if you increase the heat. You'll be able to dissolve more in it, okay, more in the water. Number 12, on which property of solutions does the concept of concentration rely? Well, concentration, remember, again, if I have a beaker of liquid here, there's my water, and if I put in some sugar or salt or whatever, well, remember that sugar is not just going to stay in a clump down here. It's going to dissolve. It's going to spread out. Okay? It's going to completely spread out, and that's because these particles are constantly moving. So the property of solutions that allows for the concentration to be basically equal throughout this particular solution is the idea that things mix. Remember we said that is what? That's diffusion. So the mixing of particles, because those particles are constantly moving, diffusion allows for the solution to have equal concentration throughout. Okay? So let's look at concentration. Let's look at molarity and molality and talk a little bit about those values. Okay? So number 13 says if you dissolve 2 moles of, this is potassium iodide, in 1 liter of water, will you get a 2 molar solution? Well, let's remind ourselves this capital M means molars. That's molar, and that's the unit anyways. A molar is the unit for molarity. Excuse me. And to find molarity, you take the mass of the solute and you divide that by, oh sorry, not the mass, sorry, my fault. Moles of the solute, I apologize, the moles of the solute, and divide it by liters of the solution. Okay? So, notice it doesn't say liters of the solvent. It's not liters of the water. It's liters of the total solution after you've made the solution. So if you have, again, here's our beaker, and I have a liter of water. That's 1 liter of water already there. Okay? And if I take then some potassium iodide and I put it in there, guess what's going to happen to the volume of this? And I'm going to add more. The volume is going to go up. So now I don't have a liter anymore. I have more than a liter. Okay? I have 1 liter plus more. I have more than a liter. So now I can't say that I have, if I put in 2 moles, now I have 2 moles, but my volume down here, my solution volume, is like 1.1 liters. Well, that's not going to be a 2 molar solution. 2 divided by 1.1 is going to be less than 2. This volume went up. It was a liter of water, but then I added the potassium iodide and the volume went up to make it more than a liter. So in order to make this solution, what you would have to do is you actually would start with less than a liter of water, okay, maybe 0.8 liters of water. Then you add your potassium iodide. That maybe brings it up to 0.9. I'm just throwing out numbers. Then you would add, you stir it all up, make sure it's all dissolved. Then you would add enough water to bring up the total solution to 1 liter. Okay? That's how you would make that solution to make sure it is a 2 molar and not less than 2 molar. 14. Suppose you dissolve 106 grams of sodium carbonate in enough water to make 6 liters of solution. Notice it says 6 liters of solution. That's not 6 liters of water. It means the total solution is 6 liters. What is the molarity? So capital M, molarity. Molarity is moles, in this case, of sodium carbonate divided by liters of the solution. Okay? So are we given moles of sodium carbonate? No, we're given mass. We're given the mass of sodium carbonate. So I need to take this 106 grams of sodium carbonate and I need to divide by the molar mass, because 1 mole of sodium carbonate, I have to look it up on the periodic table. So I go to the periodic table and I look for sodium. I have 2 sodiums, so I'm going to multiply its molar mass by 2. I have 1 carbon, so I'm going to add on its molar mass. And then I have 3 oxygens, so I'm going to have 3 times the molar mass of oxygen. Okay? I think sodium is around 23. I may be wrong, but you can double check on the periodic table. Carbon is 12, oxygen is 16. So I have 46 plus 12 plus 3 times 16, so that's going to be 48, right? So what is that? 60, around 106, okay? Around 106. Amazing. So we have 106 grams. Well, that is exactly what 1 mole is. From the periodic table, I found the molar mass of sodium carbonate. So it looks like I have 1 mole. So 106 grams, 106 divided by 106 is 1 mole. So the grams are going to cancel and we're going to be left with moles. Okay? So I have 1 mole and my solution is 6 liters. So to find the molarity, 1 mole over 6 liters, 1/6. I have 1/6 molar, okay? Or you can do 1 divided by 6 if you want to, but a 1/6 molar, 1/6 molar is my concentration, okay? 15. Suppose you wanted to produce 1 liter of a 3.50 molar aqueous solution of sulfuric acid. How many grams of solute are needed? So this time, again, we're working with capital M as molarity. That is moles of solute over liters of the solution. Well, what is given here? Let's look. We want to produce 1 liter. So I know this bottom number here is 1 liter. Okay? And I'm given the concentration, 3.5 molar. That's the molarity. I'm given that. So from this, I should be able to figure out the moles of solute, and then from the moles, I should be able to go to the grams of solute. So let's take this equation and put in what we know. 3.5 molar equals moles of solute divided by the liters of solution, which is just 1. So that means if I have just 1 liter and it's a 3.5 molar solution, I must have 3.5 moles. If I multiply both sides by 1, right, then my number of moles here has to equal 3.5. Now, 3.5 moles of this particular compound has what mass? This is where I'm going to use the periodic table and multiply by the molar mass of H2SO4. So I have to look on the periodic table. I have 2 hydrogens. I have 1 sulfur, and I have 4 oxygens. Okay, so a molar mass of hydrogen is 1. Molar mass of sulfur is 32. And each oxygen here is 16. So 232, I got 2 plus 32, 4 times 16, 40, and that's 64, right? So that's 96, 98 if I did the math right there. So moles are going to cancel. I have to take 98 times 3.5. So 98 times 3.5 is going to give me my answer right here. You can do that on your calculator, and that will tell you the grams of your solute that you needed in order to make a 3.5 molar solution, a 1 liter solution with the molarity of 3.5 molar. Okay? All right, 16. This says balanced equation. Why do we balance equation? Because we have to know the ratio in which the reactants and products are going to react in any equation, any reaction, I mean. Okay? So let's see if we can balance this correctly here. Let's start with the PO4. Do you see how this is a group here? You may hopefully recognize this as a polyatomic ion. So that's PO4. Notice there's another PO4 over here. There are actually 2 of them. So I want to definitely double this first reactant so that I have the same number of PO4s on both sides. Okay? All right. And let's see here. That gives me, now the other trick I'm going to do, I see there's an OH here. Inside of water, I'm going to write water like this. Instead of H2O, I'm going to write it as HOH. It's still H2O, but see there's a hydroxide there, there's hydroxide here. That way I can kind of treat it as a group. It makes it a little easier, in my opinion. So notice there are 2 hydroxides here, okay? There's a hydroxide OH, and there's 2 of them. There's only 1 on this side. So I think I'm going to have to double this, but maybe even more than that. So we'll see here. Actually, I think I want to do the calciums next. Notice there are 3 calciums here. There's only 1 there. So I'm going to triple this guy. Okay, now let's deal with the hydroxides. Let's see if it, and the hydrogens. Let's see if this works out. So here, this 3 triples the number of calciums, but it also is going to triple the hydroxides, which already were 2. So I had 2 hydroxides in the formula, but then that's tripled, so that's 6. So I'm going to have to put 6 here to get 6 hydroxides there. That gives me 6 hydrogens, and oh, look at that, perfect. 2 times that, 3, 6 hydrogens. So it is now balanced. 2, 3, 1, 6. That is the ratio in which this reaction occurs. It says, what mass of each product results if 750 milliliters of 6 molar, this is phosphoric acid, react according to this equation. Okay, now here's what we're going to have to do. Remember our stoichiometry from a previous chapter? Stoichiometry is working with moles and mass to find the moles and mass of other things in the reaction. Well, notice I'm not given moles and mass here. I'm given volume and molarity. But I can find moles if I'm given volume and molarity. Look, molarity is moles of the solute over what? Volume, or liters of the solution. So I'm given the volume, I'm given the molarity, I'm given these 2 numbers, I should be able to find the moles. And then if I know the moles, I can use these mole ratios to find out how much of the other things are going to be involved in this reaction. So let's take this here. 750 milliliters, by the way, I need to convert milliliters to liters. There are 1,000 milliliters in 1 liter. So 750 is going to be 0.75 liters. Okay? So let's put in our molarity here, which is 6. Moles, that's what we're going to find. Liters is 0.750. And I'm going to multiply both sides by 0.75. to get my number of moles. Okay? So, let's see here. Let's go ahead and do this calculation together. .75, well, this is just 3/4, right? So 3/4 0.75 is 3/4. We could do that. 3/4 times 6. 3/4, that's 18 divided by 4, which is going to be 4.5. Okay, if I did that right. 4.5 is the number of moles that we have of what? Of the H3PO4. Okay, if that's an aqueous reactant there, that's phosphoric acid. But in any case, so we have 4.5 moles of H3PO4. Okay, well, we want to find out how much of this product and how much of that product are produced. Well, notice the H3PO4 and the calcium phosphate, or the Ca3PO42, they react in a 1:2 ratio. Half as many moles of calcium phosphate are produced from moles of the H3PO4, the phosphoric acid. So I'm going to convert from moles of phosphoric acid to moles of calcium phosphate. By doing what? I take half. It's 1:2 ratio. 1 is half of 2. So I need half of 4.5. 4.5 moles of H3PO4, but it's a 1:2 ratio. That is moles of calcium phosphate to moles of phosphoric acid. So I take half of that, okay? Then I need to find out the mass of that. Well, the mass of calcium phosphate, the molar mass, we have to look on the periodic table. I'm going to let you do this. You got to look up calcium. You got to have 3 calciums. Look on the periodic table, find the molar mass of calcium. You have, see this 2 right here? This applies to everything in that group. 2 phosphorus, so 2 phosphorus. Look up the periodic table, look in the periodic table, look for the molar mass of phosphorus, and you're going to have 2 times 4, 8 oxygens. All right? So find calcium, phosphorus, and oxygen. Take 3 times the calcium, get that number. Take 2 times the phosphorus, get that number. 8 times the oxygen, get that number, and add them all up, and that is going to go right here. Okay, it's going to go right there. That's the molar mass. So you would take the number of moles, see what we did here? Moles of H3PO4, cancel. Now you have moles of calcium phosphate. We're going to divide by moles of calcium phosphate and get to grams using this molar mass here. So you're going to take 4.5 divided by 2 times the value here of the molar mass, which you have found using your periodic table. And that is going to give you the mass produced from the information here on that reactant. Okay? Now you're going to do the same thing for water. 4.5 moles of H3PO4. What's the ratio here? It is a 6:2 ratio. It's actually 3 times as much. So 3 moles of water are produced for every 1 mole of the H3PO4. And then we have to multiply by the molar mass of water. Well, the molar mass of water is 18 because you've got 2 hydrogens, 2 times 1, plus the 1 oxygen, oxygen is 16, that's a total of 18 there. So 18 grams for 1 mole, and this is for water. So we went from moles of phosphoric acid to moles of water, then moles of water to mass of grams of water. Okay? So you'll take 4.5 times 3 times 18, and that is the mass of water that is produced in this reaction. Okay? That's a nice problem because it gives you a nice review of balancing equation and some stoichiometry as well as working with molarity there. Okay? All right, number 17, last one. Here, notice small m. Small m is molality. Molality is still moles of the solute, but this time it's divided by the kilograms of the solvent. Okay? So in this case, how many kilograms of water must be added to 75.5 grams of calcium nitrate to form a concentration of 0.5 molal? A molal is the unit for molality. Okay? So let's see what we're given here. We are given the actual molality. We're given this number. Okay? And we're given mass of the solute. That's the solid that you're going to dissolve in water. And we want to find out kilograms of water. We want to find this bottom number down here. Okay? So let's put in some values here. Molality is 0.5. Moles we do not know. Okay? Oh, sorry. We're going to find moles here. We're going to find moles using the mass. And the kilograms we do not know. Okay? Kilograms of water. So let's find the moles here knowing the mass of our solute. So 75.5 grams. And then we're going to have to find the molar mass of this calcium nitrate. Well, I think calcium is 23. You can check on the periodic table. So 23. Then we've got 2 nitrogens. Nitrogen, I believe, is 14. Again, you can double check me. And then you've got 2 times 3, you got 6 oxygens. Okay? So 23, 2 times 14, so we got 23, 2 times 14, 28. 6 times 16, that's 60 and another 36, that's 96. So that gives us, what, 40, 51? 51 and 96 is going to be 147, if I did that right. Okay? I think so. All right? So this is 75.5 grams, and we are going to have, for 1 mole of this calcium nitrate, it's 147 grams. Well, that's about double, right? If I look at this, if I double 70, I get 140. So 75 divided by 140, 70 divided by 40, that's about a half. I'm just estimating, but you can do the actual calculation on your calculator. So this is around a half. So I know that I have half a mole. This 75.5 grams is about a half a mole of calcium nitrate. So that's going to go in here. So now I do have my moles. Okay? And I can then solve for kilograms. I like to flip them both over. When the thing that I'm trying to find is in the denominator, you can flip both of these over. This is like over 1. Just flip them both over. Yep. All right. Now look how easy this is. See this? This has to be 1. Has to be 1 kilogram. Or you can multiply both sides by 0.5 if you want to. 0.5 divided by 1 over 0.5 is going to be 1. So 1 kilogram of water. That's what you need in order to make half a molar concentration using that mass of calcium nitrate. Okay? All right. That concludes the review questions for this chapter. As always, if you've got questions, please let me know. Please contact me so that we can work through those questions and make sure that you are understanding everything that you need to know. Okay? All right, keep up the good work.